Hello everyone. Since I'm not here today, we're going to try something new. We're going to try a lesson video. Now I'm going to try to do my best as we go through this video to leave you enough time for you to copy what you need into your fill-in-the-blank note. Now if I don't seem to leave you enough time, maybe you can have somebody in control of the video so they can stop it for a bit, and then that way everybody will have time to fill in their note completely. Now it also would be a good idea to have a ruler available if you have one, because you will need to draw lines a little later on in the video. Now otherwise, let's get started. Now hopefully you have your fill-in-the-blank note in front of you already, and you will notice that today's scientist is Bohr. So this will be a bit of a review, but remember, like with the rest of the scientists, what I want you to concentrate on are three things. First, what was available to Bohr? Then 2, what model or theory did he come up with? And then finally 3, what were the problems that still existed with his model? So let's get started. At the top of the page, let's look at the evidence he has so far. Now our last person we talked about was Planck. So Bohr does have the existence of the photon. Now the other piece of data that is also available to him, of course, is the line spectrum. And remember, even way back in grade 9, when you electrify an element, it will show off some colors. Now, if you take those colors and you take a prism to separate out those colors, you will see that each element will also produce specific lines of color. Now, the element that Bohr wants to concentrate on is hydrogen, and that's because it has a very simple system and only has one electron. And so the hydrogen spectrum is also very simple. It has just 4 lines. It has a violet line and a blue-violet line, or also called indigo. It has a blue-green line, and it has a red line. So we're going to see how Bohr uses the energy of these lines and comes up with this model. Now I'm just going to give you a few seconds to make sure that you've copied everything down here correctly. And let's try now to look at Bohr's postulates. Now Bohr has 3 postulates, and you should be familiar with these 3 as well. So the first one, of course, is that the electrons orbit the nucleus, similar to a planetary system. Postulate number 2, we know that the electrons can only exist in certain orbits which have very specific amount of energy. Now these orbits, remember, are also called shells or levels. Now the last postulate, the electrons can jump from one energy level to the next, but they either require or will release energy when they do so. And this energy can come in any form that belongs in the electromagnetic spectrum, but the key one that Bohr is going to use is the light energy that's coming off, because at this time in history, the only technology they have is what they can see. And so light energy is the only energy they know that these atoms are emitting. Now I'll just give you another few seconds here to try and copy this down. Now, if we move on to the next bit, we know there's specific energies for each of our levels, but remember, the closer you are to the nucleus, the lower the energy is, and then of course, the farther you get from the nucleus, the level has higher energy. If you want to move from a lower energy to a higher energy, that requires energy to do so. And remember, that is called being in an excited state for the electron. Now, if the electron falls back down in an energy level, that means it will emit some energy, become closer to the nucleus, and we call that the ground state. So remember, ground state is where all electrons actually prefer to be. Now let's look at an analogy that relates to how the electron moves up and down. So it's just like walking up and down a set of stairs. So you can see in our next diagram, we have walking up and down the set of stairs, and we have the electron stairs. Now you'll notice in your diagram, I just boxed off numbers 1, 2, and 3, and then gave you some room below the diagram to place what those mean. My screen is going to look a little different because I'm going to put the words right in the block onto my diagram. So your point 1 would therefore be looking at either coming down the stairs yourself or an electron moving from a higher energy to a lower energy. We already know it releases a specific amount of energy to do so. Now coming down the stairs, we can hear that release of energy because our foot will make sound as it hits the step below. And for an electron, that could be a release of light or X-rays or any of the other forms in the electromagnetic spectrum. Now to go up an energy level, or as you move up the stairs, it requires a specific amount of energy. As you move up a set of stairs, you're actually using the energy that you obtained by eating food. And for our electron to move up a set of stairs, it also requires energy. Typically, this comes in the form of electricity or UV radiation, etc. Now, one of the key points to the analogy, though, just like you can't stop partway up a step, because typically you trip and you fall back down, the same thing is going to happen with an electron. If it only has enough energy to make it partway up a step, it just basically falls back down. So an electron can never exist between the energy levels. They have to be right on the energy levels. Now, as we move to the next diagram on page 3, you see I've drawn the steps for our electron. Different from a normal pair of stairs, the electron stairs are not consistent in the amount of energy between each of the levels. Recall that the first level up to the second level is actually the biggest jump. And as you go farther and farther from the nucleus, the stairs get closer and closer together. So let's now consider giving electricity to a hydrogen atom. Its one electron is going to raise up in the energy levels due to that electricity. And so let's say if we've got a number of hydrogen atoms, they've all been electrified, and all their electrons are now at level 6. Being at level 6, they don't want to stay there. They want to come back to their ground state. And so they will do that, but their path to get down to that ground state, which for the hydrogen electron is energy level 1, can be done in multiple ways. So for example, it could go one step at a time until it finally reaches its ground state of level 1. But just like many students like to do, take 2 steps at a time, well, so can the electron and make its way down to its energy level 1. Now, if you're really adventurous, you could jump all the way down to the ground level in 1 step, and so can the electron. Mind you, it's safer for an electron to do this. Now, as it does jump down those steps, do realize that it is spitting out a specific amount of energy. And so if an electron does jump from level 6 down to level 2, Bohr has designed his model such that that jump gives you violet light. So it matches the energy of violet light. Now, if an electron jumps down from level 5 to level 2, it happens to match the energy for that indigo light. And then the next 2 jumps, going from 4 down to 2, well, that gives you the blue-green, and then 3 down to 2, that gives you the red light. And notice that those lines match the line spectrum for hydrogen. Now, these 4 are not the only possibilities for an electron at level 6. In fact, there's a number of jumps that are actually bigger than violet light. And then, of course, a number of jumps that are less than red light. Now, during Bohr's time, they did not have the technology to actually see these lines. And then little later on, they did gain the technology to be able to see ultraviolet and eventually infrared. And once that technology was discovered, they went back and looked at Bohr's model and actually found the lines to exist there. Now, this is excellent for Bohr's model because he was able to predict something that he couldn't see at the time, but then eventually, when you were able to see it, there it was. And that's why Bohr's model is so good. Now, I'll give you a little bit of time here to try and draw all the lines down, and then we will continue. Now, Bohr did predict where all the energy levels should be for his hydrogen atom, and he was able to explain at least the line spectrum for certain jumps that happened. But he also mathematically came up with an equation that would state how many electrons would exist in each level. Now, we're used to how many electrons are in each level, but let's use this equation and see how it works. So he determined that if you take 2 times the energy level number squared, you'll get how many electrons will exist in that orbit. So for example, if we start with energy level 1, that'll be 2 times 1 squared, and that gives us, of course, 2. And we've known this since grade 9. First energy level can only fit 2 electrons. That's because it's the lowest of the energy levels, so small amount of energy exists there, and it is really tight to the nucleus, so it's a small orbit. Moving on to energy level 2, that would be 2 times 2 squared. That gives us 8 electrons, as we already know too. Now what I want you to do next is calculate out how many electrons should be in energy level 3 and energy level 4. So take a little bit of time and do that now. Okay, so what you should have gotten for energy level 3 is 18 electrons, and for energy level 4, 32. Now, I know when we did Bohr-Rutherford diagrams that it was 2, 8, and 8, but you also know about SPDF. Now, Bohr didn't, so his prediction was that there should be 18 electrons within the energy level 3. You knowing SPDF, though, if you do add up the electrons in energy level 3, so it does contain an S, that's 2 electrons. It does contain a P, that's 6 electrons, so we're now up to 8. But energy level 3 also contains a D level, which contains 10 electrons. And so that makes 18 electrons. So see, Bohr was able to predict something that he didn't even know anything about again. And finally, we get down to the problems with Bohr's model at this time. First problem, it only seemed to work for hydrogen. He tried other elements, but was able to get a couple of the lines correct, but he couldn't get the full line spectrums to match when he did the other elements. Second, the nucleus still really has a problem with all that positive stuff inside it, even though they did find the neutrons, which kind of buffers things inside. But there still is that nucleus problem. Then third, bonding and compounds, of course, are still an issue. So it's still going to take a little bit more time before we get answers for that. Now next, what I would like to do is we're just going to do a little review now on Bohr-Rutherford diagrams. We can bring a couple of things together now. Now I know we did these way back in grade 9, but you still should understand where they come from. But we're also going to match them with Lewis diagrams, which are far more useful because they did eventually find out that only the valence electrons do the chemistry. And so we'll do some Bohr-Rutherford diagram and match it with a Lewis diagram, and then remind you how we can handle these when they're in ion form as well. So let's take a look at an element like oxygen. Now, off the periodic table, we know oxygen has an atomic number of 8, which means it has 8 protons. It also has a mass number of 16, and 16 minus the 8 protons gives us 8 neutrons. Now I said oxygen itself, so we assume that it's neutral, so therefore it's going to have 8 electrons as well. Typically what we do is put protons and neutrons in the center, but this year we're not going to even worry about that. Just put the symbol of the element in the center, and then we're going to draw the first energy level, and we're going to place 2 of the 8 electrons in there. And then that fills up that shell because we know only 2 can fit in the first energy level. So we move on to the next one, and we're going to place the rest of the 6 electrons that are remaining. And so just remember that when you do fill up your energy level, you should be putting 1 electron into each side, like if the element was in a box, and then pair up if you need to. And so that's the Bohr-Rutherford diagram for oxygen. Now the Lewis diagram is just the symbol, and because oxygen comes from column 16, and therefore 6 valence electrons, and so all we do is put those 6 electrons around the symbol, and do remember, fill up each side of the symbol first, and then start pairing your electrons. And there is the Lewis diagram for oxygen. Now, let's consider what happens when oxygen becomes its 2- ion. So remember, on both diagrams, all you're going to do is add 2 electrons. But don't forget, if it is a charged atom, you're going to need square brackets around your Bohr diagram and your Lewis diagrams, and then note what the charge is. So now we've come to the end of our video lesson. I want you to rewind back or stop or do whatever you need to make sure that everybody in class has their note complete. And now you can work on your homework, and we'll take everything up in class tomorrow. I will also take any questions you have about the note today as well to make sure we clarify everything. I know with the video that's a little harder to do, but we'll do the best we can. So have a good day, and we will see you tomorrow.